So next up, we have Francesco from Eolo, and Francesco will tell us about the BLU project in Eolo. So the floor is yours, Francesco.
Yeah, thank you very much. So, as said, I'm Francesco Alberti. I'm a software...
If you can take your seats, please. Thanks very much. Sorry, thanks.
No problem. So, I'm working as a software engineer in Eolo, and so I would like to present the BLU project. Is a project we are running in Eolo since a few years, and the project targets the definition and the implementation of the SDN infrastructure of the Eolo network. So let me briefly acknowledge the work of my colleague also. So beside me, Patrizio, Simone, Mattia, and Alberto are also working in this project. And by the way, Simone, Mattia, and Alberto are here in the audience. So guys, if you want to raise the hand, okay, if you have nasty questions, you can ask them. Okay, so the outline of the talk is very simple. The first part of the talk speaks about the Eolo network. So the Eolo network has some very specific features, and those features raise some challenges. And we need to face these challenges in order to have an efficient solution, in order to make the network working nicely. The second section defines the tools, or present the tools that we identified, and we think these tools are the best ones we could get in order to address the challenges. And third section finally say, how can we combine these tools? What are the solutions we can devise for addressing such challenges? So now, speaking about the Eolo network. So the Eolo network was born roughly 10 years ago in the Varese area of Lombardy, so very northern part of Italy. And it was to bring a broadband connection for rural areas. That was the goal there. And then from 2006, it spread out. And today we're covering more than 90% of northern part of Italy and more than 50% of central Italy. We have actually 250,000 customers. So this is an underestimate. And okay, we have several services for our customers. And I think we are doing pretty well job. So we have 13,000 new customers per month, and we kept this pace for several months. So we hope to even improve this number. Now, what does it mean we are covering part of Italy? Well, we are bringing internet connection to the customers by means of these towers. So these are based on civil stations, and they have, oversimplifying the structure of a BTS. A BTS has some devices for creating the links at the top. So you have point-to-point links. Usually are these links that connect together the BTSs. And then you have point-to-multipoint links, which are those allowing the customers to connect to the internet. To the ground, you have network devices, router switches, and energy station, like, for example, batteries. OK, so Eolo is a fixed wireless access, and the map you see on the right side of the slide is not like a fancy graph. It is actually, if we depict a BLU node where we have a BTS, we get the shape really of the Italian country. And the edges of this graph are the links there among the BTSs. And the interesting point is that except a very few links, which are those connecting the farthest point of the network, the longest links, all the other links are wireless links. So our backhaul network is, for the vast majority, made by wireless links. OK, so why we ended up in such a situation? Well, here there are two histograms depicting the number of BTS, the histogram on the left, at a given distance from the core, and on the right we are depicting the average mesh factor for the BTSs on the left, always in terms of distance of the core. Why we ended up in that situation? Well, basically because we followed an opportunistic approach, which means that once we identified the site where it was convenient to have a new BTS, then we tried to establish a link with all the other BTS that were in line of sight and also were reasonably close to the new one. And we ended up having 500 BTSs at 4 hops from the core. And if you look at the numbers on the histogram on the right, you see that if we go 8 hops away from the core, you still get a quite high average mesh factor. So it means that after 8 wireless hops, you still have BTSs with 2 backhaul links over there. Now, if you take a different perspective of the network, you get this graph. And what this graph is showing is the diameter of our network. So here, BTSs are depicted in circles, and every circle shows all the BTSs at that given distance from the core. And distance here, I mean like the number of hops of the shortest path. And the network of the diameter of our network is 23 hops, which is quite large. Yet another specific feature of our network. So if you want to depict the number of LLDP events you may register in the network, and you take a window of 2 days, you may end up with this graph that shows that we had at most 16 minutes without topology change, which means that the network is really very dynamic. The topology changes quite fastly. Okay. One of the reasons that justifies this phenomenon is that wireless link may suffer bad weather condition. Okay, and so since we're covering large part of Italy, it may happen then in one part of Italy there is a storm or something like that, and that causes problems to the wireless link in that position. So this is a main overview of the network. To address these challenges, we thought about which kind of tools we could use, and when we thought about those tools, we had the ambition of thinking about the entire stack, starting from the hardware and up till the business logic we could implement in an SDN controller. And so we ended up in 3 main components, which are, okay, the routers, so the hardware we're selecting to be installed on our BTSs, the operating system that is running on these routers, and then the SDN controller in the end. Starting from the hardware. So a few years ago, we agreed with a US company called Tylera to build for us a few thousand units of these routers. And these have a multi-core CPU, so a decent amount of RAM and disk that allow us to deploy some applications. They do not require, importantly, a huge amount of power. So recall that these guys are installed on BTSs that may be on mountains or in very remote areas, and you cannot rely on having huge amount of power there to run the routers. And so once we got them, we tested the machines in order to check whether they were compliant with some standards, so whether they were working correctly under strong electromagnetic fields, or also with quite harsh temperatures, as they may get, for example, up in the mountains in winter, or under the sun in the Pianura Padana. So on the top of the hardware, we needed to choose an operating system. And the operating system we are running is, of course, a Linux-based distribution. And it is a Linux-based distribution customized by a French company called Sixwind. So what we agreed to have on our operating system called BLU OS is some standard tools that I'm pretty sure everybody knows, like OpenVSwitch, we have a PvP daemon, DHCP relay, routing daemons, and also, importantly, a framework made by Sixwind that allow us to to squeeze the CPU of these routers as much as we can. And what this framework does, it allows to exploit the multi-core architecture, and it has a user space data plane, and we can also deeply configure such machines. So we can assign different cores to pull out the frames getting in on the ports, and then the core is responsible for the packets that is taking out from the port until it either drop or send the packet out. And so we can configure such machines in terms of the kind of traffic they're handling. For example, we can have distributions of our operating system that is tailored for the BTSs with a lot of access clients, access sectors on the top, and so the kind of traffic they will get will be different from the kind of traffic that the BTSs, which are very close to the core, has. For example, a BTS which is really close to the core may have a 10 gig port receiving much of the traffic and then spreading out this traffic to the other ports. A blue router under a BTS with a lot of access interfaces will have a lot of incoming requests and then will have to spread out the downlink traffic to the clients. They would need different configuration for sure. Now, this is what we get from 6Wind. On the top of it, since we have the source code, we can implement tons of customizations. And so based on the statistics and on the analysis we ran from the way these guys were working, we had to implement some optimizations, let's say, in both, for example, Open vSwitch, and there are a few slides later about which kind of optimization we had to implement. We implemented some RFCs inside Quagga, the BGP daemon. We also added some kind of smartness on the Blue routers. So the Blue router, since they are installed in very remote areas, they need to be as reliable as possible. So in case of misconfiguration, the Blue router can automatically check the configuration, understand whether the configuration is corrupted or not, and restore a safe configuration such that we can reconfigure it from the headquarters. There are also many, many monitoring daemons we have on the Blue routers, and these daemons take details about, for example, LDP neighboring, so we can build a topology. We can register by querying the radios on the top of the BTS the bandwidth. So recall we have wireless links, so the bandwidth of a wireless link may vary during time. We can also send to the core the amount of traffic each Blue is processing, like the received traffic for each interface and the traffic exiting from the router for each interface. And also differentiate the backhaul traffic from the access traffic. So then on top of the operating system, the SDN controller. So now, the main reason for having an extra software layer between you and the machine, well, we heard in the talks before, there are many, many reasons. One is, of course, avoid or limit as much as you can human error. So limit the fact that somebody is configuring or handling by hand via SSH the router, and there are maybe issues about misconfiguration. So we build this tool in-house, and this tool, Alberto, is doing a very great job. And what the SDN controller has, it has all the features you may want to have, like a parallel engine for executing your commands on multiple routers at the same time. You can schedule the commands for night updates. So if you have very high load commands to be executed, you can run them at the hour you want. It has a way to check whether the commands you run succeeded, and so you can commit the changes or not. So you need to roll back to a previous configuration. It also collects and analyzes all the data that the Blue router sends to the controller. And so it knows in quasi-real time the topology of our network, where statistics, logs, error messages, and so on. So I have a few screenshots just showing what it looks like. For example, here there are the queue of commands that are ready to be executed. Some of them have been already executed, some are waiting. You can check what is going on in real time. You can edit the configuration of the router directly on the SDN controller, and then this guy will apply the new configuration on all the routers. We'll also check if the configuration is consistent, doesn't introduce bugs. We have a CLI with some kind of SQ-like syntax, and we also have some auto-completion facilities, so it's easier and very convenient when you're typing in the commands to get advices on which kind of commands you're searching for. And we have plenty of statistics, as I said. So here, for example, you can see all the interfaces of a BLU router, and for each interface you can get the configuration, the amount of traffic it is transmitting, receiving, and so on. You can check the usage of the cores of the CPU, for example, and you can also check, for example, the temperature of the board. So you have full control of your network in this way. Now, speaking now about the solutions we devised, this is was not an easy task and still is not over. So we're getting there to a time where our network will behave nicely and we will be able to take out everything. And this is kind of the story, so the past, the present, and the future of our network. We started with a very scary news, so that our network grew up as a single pervulance spanning tree layer 2 domain. And so if you think about having more than 2,000 BTSs around and more than 250,000 customers, so this means a huge amount of MAC addresses going around. And then you need to question yourself, where should you put the PEP daemon, the SCP relay, how to balance overloaded links, so how do the traffic engineering. The first solution we had in mind, and goes under the name of phase 1, introduced these features, like to reduce the number of MAC addresses, we had the PEP server and the HTTP relay directly on the BLU. And this, of course, prevent some MAC addresses to be seen by the core, for example. And then each BLU advertises to the core the IP pools he is providing to the customers. How to balance the traffic? So we can have multiple backhaul VLANs. And so by playing with the cost of the ports for the different VLAN, you can create different spanning trees and then balance this way the traffic. Remember that we have a very dense and highly meshed network, so we have many, many paths we can exploit to reach a final destination. Okay, and so this solution kind of works, more or less, but the main issue is that we didn't find a way to automatically change the cost. So there are people in Eolo looking at the cost of the ports and trying to tweak them, to play with them in order to find different spanning trees and balance the traffic. And also OVS suffers the high number of MAC addresses. So for each BLU, the MAC address table is more than 1,000 of MAC address long. And this is kind of an issue because OVS has some revalidators going on that check the flow it has in data plane and try to understand whether the flows need to be refreshed or changed or deleted and so on. So just to explain why OVS behaves badly. So suppose you have two BLU routers, the one on the left and the one on the right. They want to speak with each other, and the only way to do that is by flowing through the one in the middle. Then the one in the middle, the OVS on this guy, will create two flows, matching precisely the source MAC address and the destination MAC address for both flows. So there is one flow, the first one, matching the traffic coming in from the guy on the left, going to the BLU router on the right, and the second flow matches the traffic coming back. And so this is going to explode. It's quadratic in the number of MAC addresses at most. And if you have multiple VLANs and different kind of traffic like ARP request and other things, it simply is unmanageable. Okay, so OVS really struggle. And one thing you can do to limit this issue is actually patch OVS in order to make him forgetting about the source MAC address, for example. And this makes the number of flows linear in terms of the MAC addresses that are going around. Okay, so this seems to be quite an easy patch to do. The main issue we had here is that the traffic is not handled by OVS itself, but is handled by the DPDK framework that 6Wind made. So the way it works is that OVS taints the flow table of this framework, DPDK framework, and then the traffic is handled by this other guy. And so OVS is aware only of the traffic that doesn't match any flow. And by doing that, so by abstracting away the source MAC address, then OVS is not able to learn anymore where the MAC addresses are because it doesn't see the traffic matches. So if this guy speaks with this one and then comes this other one, the new traffic will still match the flow we had before because the source MAC address is not important anymore. So we had to play a bit with these two guys and adapt the solution in such a way that now the DPDK framework has some MAC learning feature and then pushes back to OVS the MAC addresses with the correct port where they are speaking. So this patch had quite an impact for us. If you look at the number of flows that OVS was entering before the patch, we had around more than 800 flows per second computed by OVS. With this patch, we decreased the number under 100. So it means we had almost 2 orders of magnitude of improvement. And this is the improvement on the number of the flows. The overall behavior of the router is that we get a much more stable machine. So now we had less flows. The flows we had were heated much more, so refreshed less, and we had very stable machine. And we could survive quite a lot of time with this patch. So we had the time to look at the second phase, so how to get out from layer 2 and move on. And the second phase, so we thought about our SDN controller, so what the SDN controller knows. The SDN controller knows basically the link capacity, as I said before. It knows the residual backhaul bandwidth for each link, and also knows the desired bandwidth. It means the amount of traffic it needs to deliver to the customers. So the idea was to take all this information we already have, because we have this daemon on our routers pushing back to the SDN controller, feed all this data into an optimizer. The optimizer run and perform some kind of search, and then it comes out with all the routes for the traffic we need to handle. Okay. And then, so with this set of routes, we can inform the BLU routers on the correct flows to handling the traffic. And what we can do also, we can use this extension of BGP, so RFC 3107, that allows us to advertise a neighbor with an MPLS label to the core, such that the downlink traffic enters our network with a tag. The tag is the destination BLU, and then the SDN controller instructed all the BLUs on how to treat the traffic with that label. So just to make an example, suppose we have this very simple topology, and these links are like fiber links, so they have 1 gigabit capacity. These other links are wireless links, so they have smaller capacity, and we want to deliver, so this BLU R7 needs to deliver 400 megabit per second of traffic to the customers. So we can feed all this information into the optimizer, and then the optimizer comes up and say, okay, we can write in our network this flow, okay? And how it does? Well, simply it instructs the core to label the traffic with the correct label, L7. It instructs the router in the middle for taking the traffic coming in on port 2, for example. Suppose this is port 2, and tagged with the correct label L7, and take the traffic out on this port, and then instruct this router to do the turn, and so the traffic gets delivered. Now, this works pretty nicely, except that if this link then suddenly becomes small, too small to take all the traffic to the destination, you need to compute another solution. So the controller knows in quasi-real time that this link is not big enough, so runs again, computes another path. And then what it has to do now is to go, okay, the core doesn't need to change the instruction, but it needs to delete this flow, and the slides are not displaying the line in the middle, but there is a line, so this flow gets deleted. This one changes the input port because first the traffic was coming here, now it's coming from this other interface, and then we have two new flows, okay? And this restores the traffic. What are the bad things about this solution? So, first of all, the open flow granularity is rather small. So every time you need to compute again a new flow, you need to instruct all the routers for the new flow and then patch all the routers you previously instruct on how to treat that traffic. And then you need to do that every time the network changes. And as I showed before, it can happen quite fastly in our network. Furthermore, you need to ensure that the upgrades are atomic. So you don't want to leave the network in an inconsistent state where half of the network has been programmed to treat the new traffic with the new flows and the other half is left with the back one. And how to do this in practice is definitely non-trivial. Last but not least, there is no big red button that we could push in case of troubles. Suppose we find a bug in the optimizer, for example, or suppose we are not understanding very well what the optimizer is computing. How to stop the things and revert to a safe situation where we can debug nicely what is happening and then reapply one by one the optimization. In this case, there is no such a big red button. Okay, so we have to stop a bit and think again about the next step to be done to move out from our per VLAN spanning tree layer 2 domain. And so we get to the phase 3 that improves the phase 2. What the phase 3 does, well, it follows the segment routing philosophy. And in fact, we didn't want to trash everything phase 2 brought to us because some ideas were very nice, like using RFC 107 to tag the traffic was nice. It was nice also to use OVS to treat the traffic, so we already have much of the work done inside our controller. What was bad, it was that the network was completely passive with respect to the SDN controller. So we wanted to add back to the network part of like smartness or a way for the network to survive alone without having the need of being taught every time on what to do. And the idea we had was to have an IGP running on the BLU routers. In fact, we would like to have like eBGP sessions between our BLU routers and then use RFC 3107 for advertise an MPLS label for each prefix. Then we still are tagging with the right prefix from the core by making updates, BGP updates with the RFC 3107. But then, now the big news is that nobody has to tell the routers on how to treat the traffic, but the BGP daemon is tainting the OVS flows. So BGP, once it converges, it learns the next stop for all the destination it knows, and then based on the active routing table, it can push to OVS the flows for handling the traffic with the correct label. Okay, so just to make an example, so if we go back to the network we had before, when BGP converges, all the routers in the network learn how to treat the traffic that needs to go to R7, and do it by adding in OVS the flows that say if you need to push traffic with label MPLS L7, you need to follow the shortest path as BGP computes. Okay, and so if you want to send traffic, you don't even need to optimize the network. The traffic goes following the shortest path. Now, how to optimize the traffic? So in case you saturate a link, what you can do. So we need to have one more information at the SDN controller, which means that we need the SDN controller to be aware of the routing tables of each BLU. Okay, and now the SDN controller can take, again, all this information, feed this information inside an optimizer, but just computing an upgrade or a better path for those flows that are overloading some links. And the way it can compute an optimized path is not by source routing, hop by hop, the traffic, but you can just find a waypoint, maybe 2 waypoints in the network, and force the traffic to go by such waypoints, okay? And finally, it doesn't need to instruct the network, but just the core. How you would do that? So we are in this situation, and when BGP converges, all the routers learn not only how to reach R7, but also how to reach R6. And so all the router will have an OVS flow that say, if you want to reach R6, so if the traffic is tagged with label L6, you need to follow this path. And now, if this link goes down, and so we're not able to transmit that amount of traffic over there, the optimizer may say, okay, so let's just send the traffic first to R6 and then up to R7. And how we can do that? Just by instructing the core of having a label L6 on top of L7. And so when the traffic exits, it will be treated according to L6. We go there, R6 pops away the label for itself, and then we'll transmit the traffic up to R7. So this is the idea for the third phase. There are very good point in this phase. First, the routers do not need to be instructed on what to do. They automatically learn how to treat the traffic. And then the optimizer comes into play only if you have congestion. So if the network doesn't have congestion, it doesn't need to optimize anything. And when you need to optimize the things, you may have tons of tools at your disposal for writing a good optimizer that quickly finds a new way. So you can have linear program, SMT, and a lot of heuristics, really a lot of heuristics you can implement. Finally, what we were missing before was a big red button to be pushed in case of troubles. Now we do have that button. And simply turning off the optimizer, just leaving the traffic flowing through the shortest path, is the safe situation where we want to get back. And so we may have some overloaded links, but at least we know where the traffic is going. And in case of bad things, we can reapply the optimization maybe by hand, one by one, and see why we get into troubles and patch then the optimizer. So this is the nearest future. We had some tests in our labs, and they look promising. So we hope to be in production with this idea as soon as possible. Now, if we look at the second page of the agenda, if the first one is phase 3, the second page we have different points, like a new hardware. So on many sites, well, many sites, on some sites, we ended up piling more BLU, like we have sites with 3 or 4 BLUs, and the reason is that we need more 10 gig port because of the amount of traffic we're carrying. So this is no longer power efficient, as it was before. And the idea is that if we have a super BLU, we could replace the pile of 5 BLUs with one super BLU and go back to a power efficient situation. Now, we're searching among like x86 architectures, and we will port all the things we wrote for the tile architecture of the actual BLUs. Next, we could take into consideration like delay-aware traffic. And so since we have full control of the code that is running on the BLUs, we could install like daemons measuring the delay of the link and took this delay in consideration when optimizing the traffic. And so finding a very fast route for the delay-aware traffic, and maybe a less good traffic in terms of delay for the delay unaware traffic. Next, we also almost consider downlink traffic, so traffic going from the core to the customers. What if we want 2 BLU to speak to each other? Then with phase 3, this comes almost for free. And the only thing the source BLU has to do is tag the traffic with the destination label, or can be also optimized with the stack of label, depending on what the optimizer computes. Okay, so this was the BLU project, and with what we have done in the past, and what is the agenda for the future. And of course, we would like to take questions if there are, of course, and also, if you're interested in this project, do write us, get in contact with us, and we would love to hear your feedback on this. So, thank you very much.
So, any question for Francesco?
I'm Octavio from Fastnet. I would like to ask you, as far as I understand, the network is an SDN network with routers and a controller or several controllers. Just wonder how difficult it is to manage with this new approach, the network, and how easy it is to troubleshoot issues.
Yeah, it's very nice question. Well, so the good point is that we built the SDN controller. So if we need to have some kind of functionalities to have a quick view on what is happening because we detected that this kind of problem or this kind of pattern raises up, for example, at night or at the peak of the traffic, we can implement it. And so it is really a kind of keeping the network monitored with the tools we already developed. And then as soon as we get to the point where we could not detect immediately what is happening, we just find a way to implement inside our SDN controller the new function that we need. And yeah, it's just a matter of writing the code. And it really depends on the kind of functionality you want to have. If it's just a matter of displaying some statistics, maybe it is simple. If it's a kind of automatic procedure that does some weird things on the BLU routers, it may need more time because you need to write the code, check the code is correct, test it on our test bed, and then go into production. So it really depends on the functionality you want to have.
Thank you.
Any other questions? Actually, I have one for you. Absolutely non-technical. So I think maybe it's even a couple of questions related. So I start from one angle. So are you going to open source any of this? Or in other words, is this a competitive advantage you have with your competitors? Or yet another angle, how will you ensure business continuity of this thing? Because open source could be also, so building a community around things could be an answer to business continuity and scaling beyond a single team.
Okay, so yes, so we're using a lot of open source tools. And right now, the main issue we have is that in order to work with this 6-wind framework, we need to taint the products with non-GPL licenses. So like the kernel has some non-GPL modules. And so it is not immediate to understand how to like push the changes we made to the open source repositories and then keep some patches locally in order to make it working with all the facility. But I think, well, the dream of some of us is to have this happening. So in the future, find a way to contribute actively to the open source repositories.
Thanks very much, Francesco.